Alright guys, I'm going to go over some of the practice problems that I sent you on Monday. And we're going to start with just the sums practice. Now not all of them can use the rules and the properties that we came up with in Appendix E to evaluate. It's just the idea of evaluating them by plugging in your first term, then plugging in the next integer, then the next one, all the way up until the last integer. So in this case, it'd be a pretty easy thing to evaluate by just plugging in numbers, right? So for number 1, if I plug in a 1, then I'm going to get, actually let me use green here. If I plug in a 1, then I'm going to have 1 plus 1, which is 2, times 1 minus 1, which is 0. And then I plug in a 2, and I'm going to get 3 times 1, plug in a 3, and so on. So you can see the pattern here. I'll just fill in the rest of them. And now we can evaluate these. 2 times 0 is obviously 0. Plus 3 plus 8 plus, that's an 8, plus 15 plus 24 plus 35 plus 48 plus 63, and finally plus 80, which is 276. Alright, I'm not going to do number 2. Number 2 is very similar. You just plug in the values. For number 2, though, when you're done, just so you can check, you should get 275 for that one. So to check your work. Now let's do number 3. It's a little more interesting. So with number 3, there is a pattern that's going to emerge if you look at the first couple of terms. So let's just see what's going to happen here, because we are plugging in a 1, then a 2, then a 3, then a 4, all the way up to n, but we don't know what n is. So we're going to need a representation for this end sum. But if I do start by just plugging in values, I'm going to have my first term be 6 to the first minus 6 to the 0. That's term 1. And then I'm going to have 6 to the second minus 6 to the first. And this is where you're going to notice that some cancellation is going to take place. Because if I have a positive 6 to the first here, and now I've just introduced a negative 6 to the first, those two things are going to cancel. 6 minus 6 is 0. So those will cancel. But let's continue the pattern here. Plus, because we are summing these terms together. Now I'm going to have 6 to the third minus 6 squared. And that's good news, because now we're going to notice these two terms cancel. And so this is going to continue, but this term here is never going to go away. So that term is going to come with us all along until, as this pattern continues on, we're finally going to plug in an n. And we're going to subtract from that 6 to the n minus 1. But if you take a look at the way that this pattern has progressed, it's that second term that's going to cancel with a term that's in the term before it. So this will not go away. This 6 to the n, never going to leave. And this negative 6 to the 0 is not going to leave. So if this pattern continues on and on and on, we're going to end up being left with 6 to the 0 power, a negative 6 to the 0 power, and a positive 6 to the n, which obviously should be rewritten as 6 to the n minus, and 6 to the 0 is 1. So at the end, this whole sum actually is going to equal 6 to the n minus 1. And obviously, if we really wanted a number here, once we knew n, then we would know the sum of this series. But this is another way to represent this series that's completely equivalent. All right, and now the fourth one, which sort of has a similar pattern to it. So another situation where if you continue this pattern a little bit, you're going to notice that something sort of nice happens. We're starting with plugging in a 60. So if I do that, I'm going to have 1 over 61 minus 1 over 60. Plus, now let's plug in the next integer, which would be 61. So I'll have 1 over 62 minus 1 over 61. And here you see we've got some cancellation that's happening. All right, if this continues, then I'm going to have 1 over 63 minus 1 over 62, and that's where this next term goes away. Those cancel there. And so this pattern is obviously just going to continue along. The final term that I'm going to plug in is 100, so it's going to be 1 over 101 minus 1 over 100, but as we can see from the way that this pattern has progressed, it's that negative 1 over 100 that's going to cancel, but that 1 over 101 is not going to cancel, and so I'm going to be left with these two terms when all is said and done. So here what I'm left with is the positive, wrong tool there, is the positive 1 over 101 and the negative 1 over 60. And that's not a nice number, so we would just leave it like that unless we were asked to round to a certain value. All right, the next thing I want to do is take a look at the fifth example in the practice problem set. So this was the situation with Jen's velocity, and the velocity is given in miles per hour. It's measured every 10 minutes, and this table shows the data for 1 whole hour. So since the velocity is decreasing, as you can clearly see, when we're asked to come up with a lower estimate and an upper estimate, we're going to remember that if velocity is decreasing, then it's going to be a right-hand approximation that will be a lower estimation, and a left-hand approximation that would be an upper estimation. We're not going to have to mix and match different sides of rectangles because it's consistently a decreasing function. So we're asked to find the lower and upper estimates for how far Jen traveled. I think it's a good idea here to use hours as your change in t rather than minutes. So what we're going to do is sketch a little picture of what this looks like real quickly. So we've got something like this going on, and you'll notice the way that I've labeled this here. This would be my x1 and x2, x3. It's just the way that I've got it set up, leaving this as my x0. My initial position would be right there. Okay, so I'm going to think about this in terms of what my delta t would be. We said that my change in time is 10 minutes, but I don't want to represent that in terms of minutes because I've got miles per hour here, so I want these units to be the same. So I'm going to think of that in terms of a sixth of an hour. And that's going to be my delta t. So now I can say that this distance here is 1/6, and so is this, and so on. So I've got that consistent change in t. All right, so let's do our over estimate. All right, so we'll do an upper sum. So we're going to take the distance to equal the sum of all the values when I plug in a 1 through a 6 of f of, and since this is a left-hand approximation, it's x of I minus 1, because I'm using the left side of each of these rectangles, times delta x, or in this case, what will be delta t. So we'll just draw in what this is going to look like here. My first rectangle with a left approximation is going to look like this. Okay, this is my second rectangle. My third, fourth, fifth, and my sixth. And so I'm going to represent each of those rectangles, and obviously the bottoms here as well, as my sum. So my first rectangle is obviously going to have a width of 1/6, right? We've got that here, 1/6. And my second rectangle is going to have a width of 1/6, and my third and my fourth. And so what we've started to do is to pull out that constant and look at this as delta x times the sum of all of these rectangles. And so you should be pretty comfortable with me just jumping right to that format. So I'm going to write this as 1/6 times this whole sum of all of these values. Okay, so the height of this first rectangle here is determined by f of 0, and f of 0 is 60. So that first height is 60, plus the height of my second rectangle is determined by f of 10, or f of 1/6, 10 minutes, or 1/6 of an hour. So that's going to be 55. And this pattern is going to continue. I'm going to add 50, I'm going to add 40, 35, and 25. I'm not going to add 0 though, because none of these rectangles have a height of 0. This is my over approximation. So when I do that, I'm going to end up with 1/6 times 265 which is 44.17 miles. And so remember, since we were measuring velocity here, and each of these data points was a velocity measurement, when I calculate the area under the curve, I'm getting position. Right? I'm going the opposite direction of when we were taking derivatives. Now we're going the other way. So the antiderivative of velocity is position. So I'm calculating position by getting that area under the curve. Now let's redo this, but this time we're going to use an under approximation instead of an over approximation. So I'm just going to get rid of all that. Bear with me, I don't have a larger eraser tool. All right, so we'll redo this, but I'm going to redraw these rectangles as right-hand approximations. So this is my first rectangle. And you can see why this is now going to be an under approximation, because since this function is decreasing, I now have a whole bunch of space between the curve and where these rectangles begin. So this area that I'm going to get here is going to be way less than the actual area. So that space that I'm referring to here is this space here, which is not going to be included in this calculation, but definitely would be included if I knew the actual area under the curve. So the number I'm about to get will be less than the actual area. All right, so we'll redo our sum. Our sum, which we're using to represent distance here, is still going to be the sum of 6 rectangles. This time, we're using the right endpoints times delta x. And so the way that I'm going to represent this is, again, 1/6 is the constant that I'm removing from this whole sum. And now I'm going to add the values of each of these numbers. So my first rectangle's height is no longer dictated by f of 0. It's now dictated by f of 1/6, or f of 10 minutes, which is 55. And then my second rectangle's height is dictated by f of 20 minutes, or f of 2/6. And this continues. So if I add all those up and multiply it by 1/6, I end up with 205 times 1/6, which is approximately 34.17 miles. So I know that the actual area under the curve is somewhere between 34.17 and 44.17, but by doing this over and under estimate, that gives me a window where I know that the actual number is somewhere in that range. All right? And on Thursday, we'll go over some integral representations of these Riemann sums, but that's a good review for the first portion of this unit.